Hello again, Psych 370 students, and welcome to one last video lecture for this week. Obviously, we've spent this week and last week learning about schedules of reinforcement, right? But so far, we've focused mainly on how those schedules affect behavior in fairly simple situations, where there's only one response that the animal could perform, like pressing this one bar, or pecking this one disc, or whatever. But now we're ready to start looking at more complex situations, choice situations, where the animal has more than one response that it could perform, with each response getting reinforced on a different schedule. So, situations like that are obviously more complex than the one response situations that we've been considering so far. And, guys, choice situations in the real world can be very complex. Because think about it, at any given time, you've got a choice among a huge number of different behaviors, right? You could study, you could sleep, you could text, you could watch TV, exercise, surf the web. And it goes without saying that analyzing all of the factors that influence your choices among so many different options would be an extremely difficult task. So, when I say that we're going to start looking at more complex situations, you should know that for the most part, the choice situations that psychologists have tended to focus on have been the simplest choice situations possible, where there are just two different responses that the animal can make and where each response gets reinforced on a different schedule. And to study situations like that, researchers set up what are known as concurrent schedules of reinforcement, meaning that two different schedules are in effect at the same time. So they're operating concurrently. Now, I want to make sure that you notice the difference here between this kind of arrangement with concurrent schedules of reinforcement and what you'd have with a multiple schedule of reinforcement, which I talked about last week when I was explaining why we'd see those pauses on fixed ratio schedules. So remember, in a multiple schedule, you also have two or more schedules, but those schedules take turns. They alternate so that only one schedule is actually in effect at any given time. So, in other words, with a multiple schedule, there's only one response that the animal can make, or only one response that you're actually measuring, I should say. But sometimes that response is being reinforced on one schedule, and other times it's being reinforced on a different schedule. That's how a multiple schedule of reinforcement works. However, if two schedules are concurrent, then that means that the animal has a choice between making one response, which gets reinforced on a particular schedule, or making another response, which gets reinforced on a different schedule. So when two schedules are concurrent, they're being presented simultaneously, meaning that the animal is free to switch back and forth between them. It's free to choose one over the other. And that situation is more like the choice situations that people and animals actually experience, right? So, for example, channel surfing with your TV remote is a good example of concurrent schedules because you can select any one of a number of channels. You can change the channel whenever you want to. And some channels are more interesting to you than others, meaning that watching different channels gets reinforced on different schedules. Or another good example of concurrent schedules would be talking to different people at a party. Because again, you can talk to various people, different people are available to talk to at the same time, so they're available concurrently. And you'll probably seek out certain people to talk to because you've learned that talking to them gets reinforced on a richer, denser schedule than talking to other people does. So, obviously, to present animals with choice situations like that in the lab, we need to make more than one response available to them. There needs to be more than one response that they're able to make. And the way this has most commonly been done is with pigeons in Skinner boxes, where there are two different keys that the pigeon can peck, and pecking each one gets reinforced on a different schedule of reinforcement. So, for example, in this case, with the picture on the slide here, we've got an FR10 schedule in place for the left key and an FR60 schedule for the right key. So, in other words, the pigeon can get some food for every 10 pecks of the left key and for every 60 pecks of the right key. So this is an example of concurrent schedules, but guys, concurrent ratio schedules like this aren't actually all that interesting because all the animal is really going to do is just sort of get a feel for each schedule and then settle on the richer one. So it's interesting that it's able to do that. It's kind of interesting that it's able to figure out which of these responses pays out better, which response is on the richer schedule of reinforcement. But the reason I said that concurrent ratio schedules aren't very interesting is because this animal is obviously going to stick with the left key here once it realizes that that one gets it food after fewer pecks. So it doesn't really make sense for the animal to switch in this case, right? There's no reason for the animal to abandon the left key and peck the right one instead, and it tends not to. An animal in a situation like this will wind up pecking the left key more or less exclusively. However, what's more interesting are situations involving concurrent interval schedules, because with those, it does pay for the animal to switch occasionally from one response to the other. So, for example, let's say that we have a pigeon who's pecking one key on an FI 10-second schedule, and we'll say that pecking this other key gets reinforced on an FI 60-second schedule. So, pecking the left key is going to pay off more frequently, right? So, it makes sense for the bird to favor that key. It makes sense for the bird to direct most of its responses toward that left key. But there are still going to be some times where reinforcement isn't available on that schedule, times where it could peck the left key all at once and not get reinforced for that response. And so it could spend some of that time working on the other schedule, right? Pecking the other key, the right key. And sometimes it'll be possible for the animal to get a reinforcer by pecking the right key when it couldn't get one for pecking the left key. So, to maximize the total number of reinforcers that it gets, what the animal needs to do is it should spend most of its time pecking the left key, but it should also occasionally step over to the right key and peck it. From a purely mathematical point of view, that is the strategy that makes the most sense in the long run. That's the way of allocating its time and effort that is going to give this bird the best overall payout. And the interesting thing is, that's pretty much exactly what this bird will do. So, for example, in this case, the pigeon can get about 6 times as many reinforcers from the 10-second schedule as it can from the 60-second schedule. And so it winds up making about 6 times as many responses on the left key as it does on the right key. So, in other words, it will tend to divvy up its responses between these options in just about the most efficient way possible, the way that matches the rate at which it can get reinforcers from those options. So, concurrent schedules involving interval schedules do tend to be more interesting to psychologists than those involving ratio schedules. And of course, this example involved fixed interval schedules, but animals also display the same kind of tendency when they're reinforced on concurrent variable interval schedules. For example, in a classic study on choice, Richard Herrnstein put his pigeons on several different pairs of concurrent VI schedules. In this first one, as you can see, the pigeon is on a VI 135-second schedule for pecking the left key, and it's on a VI 270-second schedule for pecking the right key. So for this pigeon, even though the delivery of reinforcers is variable and unpredictable, it still makes sense for the pigeon to devote most of its time to the richer schedule, which pecking the left key is on. But again, it should still occasionally peck the right key, even though that one is on a thinner, leaner schedule of reinforcement. Because after all, the pigeon could peck the left key exclusively, but that's not the best strategy for it in the long run. It can get more reinforcers overall by pecking both keys. Because again, sometimes a reinforcer is going to be available on this thinner schedule on the right and unavailable on this richer schedule on the left. That won't happen often, The majority of the reinforcers that the pigeon can get will come from pecking the left key, so it's going to direct the majority of its responses to that key. But it does do better in the long run by pecking both keys than it does by only pecking one. And again, the fascinating thing about all of this is the efficiency with which animals will come to distribute their responses when they're in situations like this. Even when there's only a slight difference between the two schedules, even when one is only slightly richer or thinner than the other one, animals still typically choose between them in a way that gives them something close to the best overall payout in terms of total reinforcers. So, for example, Herrnstein found that when he presented his pigeons with this choice, the one that I'm showing now on the slide, the pigeons would peck the left key about twice as frequently as they'd peck the right one. In other words, about two-thirds of their responses were directed toward the left key, and the other one-third of them were directed toward the right key. And in other pairs of concurrent schedules, Herrnstein found that animals also distributed their responses in similar ways, in ways that reflected the relative richness and thinness of each schedule. For example, when he switched the schedules so that the one for the right key was now richer than the one for the left key, he found that animals quickly went from making one-third of their responses on the right key to making two-thirds of them on that key. And in another pair of concurrent schedules, the left key was on a VI 108-second schedule, and the right one was on a VI 540-second schedule. So, before I tell you how the animals distributed their responses on those two concurrent schedules, what I want you to think about first are the maximum rates at which the animal could get reinforced for pecking those two keys. On these two variable interval schedules, the maximum reinforcer rate for pecking the left key is 5 times greater than the maximum reinforcer rate for pecking the right key, because this interval on the left is 5 times shorter than this interval on the right. So reinforcers are going to become available 5 times more frequently on this schedule on the left than they are on this schedule on the right. And accordingly, Herrnstein found that his pigeons made about 5 times more responses on the left key than they did on the right key. They pecked the left key 5 times more often than they pecked the right key. 5/6 of their responses were directed toward the left key, and the other 1/6 of their responses were directed toward the right key. Furthermore, when he reversed those schedules, he found that the pigeons reversed their response tendencies too. So, once again, the pigeons divided up their responses between those alternatives in a way that matched the rate at which they were able to get reinforcers from them. So, here's a graph of Herrnstein's results with 3 different pigeons. What we've got here is on the vertical axis, what percentage of the pigeon's total responses were left key pecks. And on the horizontal axis, we're looking at what percentage of the maximum number of reinforcers that were available from that left key. And as you can see, there's a very orderly relationship here. So the diagonal line, which I've highlighted in red, shows a perfectly linear relationship between response percentage and reinforcer percentage. And Herrnstein's data points don't all fall exactly on that line, but they're very close. This is about as close as you're going to get in actual research to a perfectly linear relationship between two variables. And so Herrnstein concluded that in a choice situation, we can predict how much or how little an animal is going to favor one of its options if we know what proportion of its reinforcers it can obtain by making that response. And guys, the more precise version of what I just said is what's known as the matching law, which is just a mathematical formulation of the idea that the extent to which you're going to favor one option over another depends on how much more often you can get reinforced by doing it instead of the other thing. In other words, the percentage of your behavior that you devote to a particular option will match the percentage of your reinforcers that you get from that option. So response percentage will match reinforcer percentage, basically. That's the matching law in a nutshell. And the actual formula describing the matching law is pretty straightforward. It looks like this. So again, this is just a mathematical way of stating that the percentage of the time you choose one option over the other, the percentage of the time you make one response instead of the other, will match the percentage of your reinforcers that you can get by performing that response. Again, response percentage will match reinforcer percentage. That's what the matching law is all about. So the left side of this equation is the response percentage side, or the response proportion side, I guess. The percentages and proportions are basically the same thing. Multiply a proportion by 100 and you've got a percentage. But anyway, on the left side of the equation here, we're looking at response proportion. So B1 is the number of times the animal makes the first response. So for example, the number of times the pigeon pecks the left key. And we're dividing that number by the total number of responses. So in the denominator here, we've got B1 again, plus B2, which represents the number of times that the animal made the other response, the second response. So the number of times the pigeon pecked the right key in the example I've been using. So the left side of the equation represents the proportion of responses that the animal directs toward a particular option. That's why I called it the response proportion side. And the right side of the equation is the reinforcer proportion side. R1 equals the number of reinforcers that the animal can get by making the first response, and R2 equals the number of reinforcers that it can get by making the second response, by choosing the second option. So for example, if the left key were on a schedule with a 20-second interval, then the pigeon could get at maximum 3 reinforcers per minute from that schedule, right? Because reinforcers are going to become available 3 times per minute on average on that schedule. So we could let R1 equal 3. And if the right key were on a schedule with a 60-second interval, then the pigeon could get at maximum 1 reinforcer per minute from that schedule. So we could let R2 equal 1. So if we take R1, which is 3, and we divide that by the quantity R1 plus R2, which is 4, then we see that 3/4 of the reinforcers that this animal can get, 75% of the reinforcers that this pigeon can get, are going to come by making that first response. It's going to be able to get 75% of its reinforcers by pecking the left key. And of course, it can get the other 25% by pecking the right key. And again, the matching law says that that reinforcer percentage is going to match the animal's response percentage. So it predicts that this animal is going to divide up its responses between these two options in a way that matches the proportion of reinforcers that it gets for those two options. So in this case, if the animal is maxing out the total number of reinforcers that it can get, then it's going to get 75% of those reinforcers by pecking the left key. So according to the matching law, it should make 75% of its responses on the left key. And it can get 25% of its reinforcers by pecking the right key. So according to the matching law, it should direct 25% of its responses to that key. So in other words, since the animal can get 3 times as many reinforcers by pecking the left key as it can by pecking the right key, it should wind up pecking the left key about 3 times as much as it pecks the right key. The percentage of the time that it chooses that left key should match the percentage of its reinforcers that it can get by performing that response. Again, that's the essence of the matching law. Now, I'm talking about the matching law so much because it has a lot of support. It isn't perfect. There are exceptions to it where the animal seems to prefer one option more strongly or less strongly than the matching law would predict. But the matching law does hold up pretty well in many different situations with different species, different behaviors, and different reinforcers. In fact, even though Herrnstein formulated the matching law based on his studies of pigeons pecking keys in Skinner boxes, it's actually been extended to human behavior in a few interesting ways. So I want to finish up this video lecture by telling you about a few of those applications of the matching law. For example, in one study college students participated in four-person discussions about drug abuse. So in this study, we've got these four-person discussion groups. But in each one of those groups, there was only one real participant, and that person would actually be interacting with three confederates, what we call confederates. So a confederate is basically somebody who pretends like they're a fellow participant, but they really aren't. They're a part of the experiment. They're like an accomplice of the experimenter, just playing a role. So in each group, there's only one real participant. They're interacting with these three confederates. And one of those confederates was basically just the moderator of the discussion. It was their job to ask questions and keep the conversation moving. But the other two confederates would occasionally receive these cues in the form of blinking lights that only they could see. And whenever a confederate received a cue like that, it meant that they were supposed to reinforce the next comment that the actual participant made. And they do that with verbal approval. So they'd say things like, "Oh, that's a good point," or "Yeah, I see what you're saying." Okay. So those two confederates had been instructed to only interact with the participant when they received one of those cues to reinforce, to approve of the participant's next comment. And guys, those cues were also programmed in such a way that one confederate received them much more often than the other one did. So the participant is going to be receiving more reinforcers from one of these confederates than they are from the other one, right? A greater proportion of the verbal approval that each participant received came from one confederate than it did from the other. And so what the researchers measured was the amount of time that each participant spent looking at and talking to each confederate. So how much of their responding during this discussion did they direct toward each of those two confederates? That's what the researchers wanted to know. And what they found was that by the end of the discussion period, there was a pretty close match between the proportion of the reinforcers that a participant got from a particular confederate and the proportion of time that that participant spent looking at or talking to that confederate. So here's a graph of the results of that study. This is based on the last 5 minutes of the 15-minute discussions that the participants had with the confederates. And as you can see, by that point in the conversation, the participants appeared to have picked up on the fact that they were getting more reinforcers. They were getting more of that verbal approval from one confederate than they were from the other. So the graph is showing the proportion of the time that each participant spent responding toward a particular confederate and the proportion of the verbal approvals, the proportion of the reinforcements that the participant received from that confederate. So again, we've got reinforcer percentage here on the horizontal axis, response percentage here on the vertical axis. The red line represents what the matching law would predict, and the dashed line is the best fitting line for this data set. And again, there's not much deviation here, indicating that the matching law did a pretty good job of predicting how these human participants were going to allocate their responses in this social situation. So the matching law has interesting things to say about how we interact with other people, about how and why we might devote more of our time and attention to some people than we do to others. But it's also been applied to sports in a few ways that, as a sports fan myself, I can't help but share with you. So, for example, one way that the matching law has been applied to sports is by using it to analyze the play calling choices of professional football teams. So, obviously, football is a pretty complicated sport, but you can view play calling as essentially a simple choice situation, right? Because the team can choose to either run the ball or to pass it. So, in this study by Derek Reed and his colleagues, they analyzed the 2004 NFL season by looking at each team's allocation of running plays versus passing plays and the number of yards that each team gained from each type of play. So, they've got two kinds of proportions for each team, right? They've got response proportions, telling them what proportion of each team's plays were runs and what proportion were passes. And they've also got reinforcer proportions, telling them what proportion of the team's yardage came from running the ball and what proportion of their yardage came from passing the ball. And they found, as you can probably guess, that those two proportions tended to match up with each other pretty well. You can see that in the graph. So if a team got a greater proportion of its yards by passing the ball, then it tended to pass the ball more often. And if it got a smaller proportion of its yards by passing the ball, then it tended to pass the ball less often. That was the overall trend. Now, the teams did show a slight bias toward running plays, meaning that they tended to run the ball more than the matching law predicted. The percentage of the time that they chose to run it slightly exceeded the percentage of the yards that they gained by running it, which, as the authors explained, could be due to the fact that when you pass the ball, you do stand to gain more yards, but you could also gain 0 yards in the case of an incompletion. And you're also more likely to turn the ball over to the other team when you pass it than you are when you run it. So, again, the matching law isn't perfect, but as you can see in the graph, it did do a pretty good job of predicting play calling choices by these American football teams. And interestingly, it did an especially good job of that when it came to the better teams. So Reed and his colleagues found that the more a team tended to deviate from the matching law in terms of how it distributed its running plays and its passing plays, the worse that team's overall win loss record tended to be. And so the takeaway, I guess, is that it could be in a team's best interest to consider the matching law a bit more carefully when it comes to deciding how they're going to divvy up their play calls. So that's a neat application of the matching law to football. And another interesting sports related application of the matching law involved 2 point and 3 point shot allocations in basketball. So the key question there, of course, is whether players will match the proportion of shots that they attempt from 3 point range to the proportion of the points that they score by shooting those shots. And by now, I'm sure you can probably guess what the answer to that question was. Players who scored a greater percentage of their points from 3 point baskets tended to attempt a greater percentage of their shots from 3 point range. So, obviously, if you find that you're getting most of your points from 3 point attempts, then you're probably going to make most of your attempts from that range. And if you find that few or none of your points are coming from 3 point baskets, then you'll probably make it so that those shots constitute a smaller proportion of your attempts. You'll probably shoot mostly 2 pointers in that case, because most of your points, most of your reinforcers are coming from choosing that alternative. So, anyway, guys, the matching law is a pretty straightforward principle, but it's an important principle because it can be applied to lots of different domains. Like I said before, it isn't perfect, but it does do a very good job in most choice situations of predicting how people and animals are going to divide their time and effort when they have to pick one behavior from among multiple options. Okay, well, that's about all I have to say about choice and the matching law. So that's going to do it for this week's video lectures. As always, please let me know if you have questions about any of this stuff, and I hope you have a great day. Take care.